Hi, I'm Professor Goins, and in this video I'm going to go over the derivative of a parametric curve. We'll start off with the geometric motivation for where the formula comes from, and then we'll do some examples of computing derivatives. Okay, so first and foremost, remember that a parametric curve is a curve in the two-dimensional plane. Could be 3 dimensions as well, or any dimension, but in our Calc 1 class we like to do everything in 2 dimensions. So a parametric curve in 2 dimensions where the x and the y coordinate are both functions of another parameter t, or of an independent variable t, and the values of t range from a to b. In particular, a point on the graph has the form, so if it starts here and ends here, and my final t value is b, then this last coordinate here would be x of b, comma, y of b. And we would say that this point refers to the coordinates, or the point when t is equal to b. So that's why along the curve I may refer to a point as just corresponding to a specific t value, but remember the actual point is x and y evaluated at that t value. All right, I take a look at this curve here. Suppose I wanted to find the slope of this tangent line, this dotted line, at the point corresponding to t equal to c. Well, what we do is we start with a secant line. So I'm going to take a point that's after this one, right? So a second point on the curve, which is going to correspond to the point c, and then plus something, so c plus h. H in this case is a positive value. So this would of course have the coordinates, x of c plus h, y of c plus h. But I can find the slope of this secant line, and then what we'll do is we can use that to construct the slope of the tangent line. So the slope of the secant line is given by the change in the y values divided by the change in the x values, just like the slope of lines that you found back in your pre-calc or algebra class. And the change in the y values, well, the y value at this point here would be y evaluated at that value of t, which is c plus h, minus the y value at this point, which would be the y coordinate evaluated at that t value, which is y of c. Then I'm going to divide that by the change in x. The change in x would be the x coordinate here, which is x evaluated at this t value, x evaluated at c plus h, minus x of c. So that would be the formula for the slope of a secant line on this curve. Again, what I'm interested in though is the slope of the tangent line. And the way I can create the tangent line from the purple line is so just sort of visually, I want this purple dot to get closer to the black dot. And the way I do that is I take this h value smaller and smaller. In other words, I'll take the limit as h approaches 0 of this expression right here. So I'm going to take the limit as h approaches 0 of what we just found. As is, we can't take the limit of that. We have to do some sort of manipulation. And the manipulation that I'm going to do in this case, I'm going to multiply the top and the bottom by 1 over h. So I'm going to distribute 1 over h to the top, 1 over h to the bottom, and let's see what we get. This would be the limit, h approaches 0. And again, this is going to look messier, but it's going to allow us to be able to construct the limit. And let's put in some grouping terms here, some grouping symbols, so we see what the numerator and denominator is. Okay, so then when I take the limit of what's inside this set of parentheses and the limit of what's inside this set of parentheses, this expression should look familiar, right? This is the difference quotient. So when I take the limit of a difference quotient, that's where we get a derivative. And so taking the limit, this would give me in the numerator the derivative of y, dy dt, and this is evaluated at this point. So evaluated when t is equal to c, and my denominator would be the derivative of x when t is equal to c. And the way that we normally would write this is I would put the evaluation top and the bottom. I really only need to do that once. So this would be the derivative of y divided by the derivative of x. And then I'll take that expression and evaluate it at c. So this would be the derivative of a parametric curve. And another notation for this is to say it's dy over dx evaluated at t is equal to c. So the derivative of a parametric curve is given by this formula here. Take the derivative of the y coordinate divided by the derivative of the x coordinate. So let's do an example and see how that will work. Let's say my parametric curve is given by the following. X is t squared plus 1, and y is going to be the sine of t. And let's say the t values range from 0 to pi. Let's say I want to find the first derivative of that. So solution. So the first derivative of this parametric curve is given by this formula right here. The derivative of a y with respect to x, I take the derivative of y with respect to t, and then I divide that by the derivative of x with respect to t. So the derivative of the y coordinate would be cosine. So this would be cosine of t divided by the derivative of the x coordinate with respect to t, which would be 2t. So there's my first derivative of that parametric curve. Let's do one more example of computing the derivative of a parametric curve, and let's do it in the context of actually finding the equation of a tangent line. All right, find the equation of the tangent line to the graph of the following parametric curve. Let's say x is equal to t cubed plus t, and y is going to be negative t to the fourth plus 5t. And let's say t ranges from 0 to 10. So find the equation of the tangent line to the graph of this parametric curve where t is equal to 1. Okay, so solution for this. Well, what we're going to have to find is the point on the graph, the point of tangency. We have to find the slope of the tangent line, and then we'll put it together and find the equation of the line. And it looks like I'm going to need some more space, so let me clean this up too. Right. First things first, let's find the point of tangency. So I'll just abbreviate that as point, but this is the point on the graph of the parametric curve for which the tangent line will be, well, tangent to. So when t is 1, that means that the x-coordinate would be x of 1, the y-coordinate would be y of 1. So when I take 1 and plug it into the coordinate function for x, that'd be 1 cubed plus 1, which would be 2. And when I plug 1 into the y-coordinate, that'd be negative 1 to the 4th plus 5 times 1, so negative 1 plus 5 would be 4. So my point of tangency would be 2, 4. For the slope, so the slope of the tangent line would be the derivative evaluated at t is equal to c. So the slope of the tangent line is the derivative of the parametric curve evaluated when t is c. So we have to find the derivative first. All right. The derivative of the parametric, again, let's write out the formula for it. It's the derivative of the y-coordinate divided by the derivative of the x-coordinate. Okay. If I take a look at the y-coordinate, I have to use the power rule and then a constant multiple rule here. So I've got negative 4t cubed and then plus 5. Technically, we use the power rule there as well, exponent of 1. And then divided by the derivative of the x-coordinate, which would be 3t squared plus 1. And therefore, my slope m would be that expression we just found, evaluated when t is equal to c. Well, t is equal to c. In this case, our c value is 1. Okay. So I plug that in, and I'm going to get 1 to the 3rd is 1, so I've got negative 4 plus 5 would be 1, divided by, plug 1 in down here, 3 times 1 squared plus 1 would be 4. So my slope is 1/4. Okay. And then finally, we find the equation of the line. And what do we have here? I've got an arbitrary point on the line, and I've got the slope of the line, so therefore we use point slope form. So y minus b, m, x minus a, where again, this is the y-coordinate, this is the x-coordinate, this is our slope. I plug those numbers in, I get y minus 4 is 1/4 times x minus 2. Distribute that through, y minus 4 is 1/4 x minus 1/4 and negative 2 would be negative 1/2. Add 4 to the other side, giving the equation of my tangent line. So then I have 4, and I'm adding that to negative 1/2. 4 is the same thing as 8/2, so this would be plus 7/2. And an additional just emphasis on the notation. We could put a subscript of a t here to emphasize that it is the equation of a tangent line.